Hi, for this video, we'll be talking about electric potential and potential difference. Now, what are these two quantities? Let's start off with electric potential. Electric potential, also called as electrostatic potential or simply potential because it's already understood that it's electric. Electric potential is, well, at any point in an electric field represented by E, electric potential energy per unit charge at that point. So electric potential is the amount of kinetic energy per unit charge or for every coulomb of charge. Electric potential is designated as V, where V is equal to electric potential divided by charge. Electric potential is a scalar quantity. Its SI unit is volt, named after Alessandro Volta, who devised one of the first electric cells. Looking at our equation, we can note that 1 volt is equal to 1 joule per coulomb. Also, electric potential can be expressed in terms of electric field, where you have voltage or electric potential is equal to electric field times the distance between a certain multiplied by the distance at a certain point, which is also equal to, where volt is also equal to Coulomb's constant times charge divided by the distance at the point surrounding a point charge. If there are several charges surrounding a point, the potential at a point due to these charges is simply the algebraic sum of the potential due to each charge. So if you look at the illustration, we have here point P, and there are 3 charges that surrounds point P. Now the total electric potential that will be experienced by point P will be the result, or will be the algebraic sum, just the sum of the electric potential due to each of these charge. This is because, as what we have mentioned earlier, V, or electric potential, can be written in terms of electric field, and electric field follows the superposition principle. In the figure, the potential V at point P due to charges Q1, Q2, and Q3 with distances R1 and R2 and R3 respectively from point P is, of course, V is equal to the voltage due to charge 1, voltage due to charge 2, and voltage due to charge 3. If you change your expression V1 to what is it equal to, which is KQ1 divided by R1. So V is equal to KQ1 divided by R1 plus KQ2 divided by R2 plus KQ3 divided by R3 in this case here in our illustration. So if we have 4 charges surrounding point P, then we will have V1 plus V2 plus V3 plus V4. Now we have electric potential difference. By the term itself, it's just the difference between the electric potential, or it's the difference in electric potential between different points or between 2 points. So potential difference is the difference in the amount of energy that charge carriers have between 2 points in a circuit. We have here VAB, which is your potential difference between point A and point B. It's equal to the work done from point A to point B divided by charge, divided by the charge, which is equal to, remember that work is equal to negative change in potential energy. So it's negative change in potential energy divided by Q0. And if you remember the previous formula that we have for voltage, where voltage is equal to the potential energy divided by the charge. So the change in potential energy is UB minus UA. And UB divided by Q0 is voltage at point B, and UA divided by Q0 is voltage at point A. Distributing our negative sign there, then we have the potential difference between point A and B is equal to VA minus VB. So let's look at an example here. A charge of 6 times 10 raised to negative 7 coulomb is transferred from infinity to point B. If the work done by electric force to do this is 1.2 times 10 raised to negative 5 joules, what will be the potential at point B? So what are our given values? We have we have Q0, we have Q0, which is equal to 6 times 10 raised to negative 7 coulombs. And then we have the work done in between the 2 points, which is 1.2 times 10 raised to negative 5 joules. Now, when you look at it, you have here transfer from infinity to point B. So it's also important to remember that potential at infinity or ground is equal to 0. Again, the potential at infinity or ground is 0. So using our equation, work from point A to point B divided by charge is equal to the difference between the voltage or between the electric potential between point A and point B. We are to solve for the potential at point B. But VA, or potential at A, is 0. Therefore, this is 0. So you're left with, to solve for VB, we have negative VB is equal to work from A to B divided by the charge. And just multiplying both sides by negative sign, by negative 1, then we get positive, and this becomes negative. So you have voltage at point B is equal to negative work from point A to point B divided by charge. And that will be 1 negative 1.2 times 10 raised to negative 5 joules over 6 times 10 raised to negative 7 coulombs. So the potential at point B is negative 20 volts. There. Another example. A point charge of negative 6 times 10 raised to negative 9 coulombs is 3 meters from point A and 5 meters from point B. Find the potential at point A and point B and how much work is done by the electric charge, or how much work is done by the charge in moving a 2 nanocoulomb particle from point A to point B. So what are our given values here? Our given values is we have the charge. For problem A, or for question A, we have the charge, which is negative 6 times 10 raised to negative 9 coulombs. And then we have the distance in point A, when it comes to point A, which is 3 meters, and the distance in point B, which is 5 meters. Now, how do we solve for your VA, or your potential at point A and potential at point B if you have your charge and your distance, or your or the distance between a certain point and the charge? So remember that potential is equal to Coulomb's constant times charge divided by your distance, or R. So if we are to solve for VA, then that would be KQ divided by RA. And your Coulomb's constant, of course, is 9 times 10 raised to 9 Newton meters squared per Coulomb squared, multiplied by your charge is negative 6 times 10 raised to negative 9 coulombs divided by 3 meters. So it will be our answer here. Your potential at point A will be negative 18 volts. Now for potential at point B, it will be KQ divided by RB. And that will be VB is equal to still 9 times 10 raised to 9 Newton meter squared per coulomb squared multiplied by negative 6 times 10 raised to negative 9 coulombs, because it's still the same charge. The only difference is that we are looking into the potential at a different point. And VB here is equal to, if you input that in your calculators, that's negative 10.8 volts. So your potential at point A is negative 18 volts, and potential at point B is negative 10.8 volts. Now for question B, how much work is done by the electric charge, or by the charge, in moving a 2 nanocoulomb particle from point A to point B? How much work will be done by the field surrounding the point charged negative 6 times 10 raised to negative 9 coulombs? For question B, we need to solve for the work done in moving a 2 nanocoulomb particle. So a 2 nanocoulomb particle is equal to 2 times 10 raised to negative 9 coulomb. What we mean here is that if we have negative 6 times 10 raised to negative 9 coulomb charge, and here's point A, and this is point B, what will be the work done if a 2 nanocoulomb charge is moved from point A to point B? Now again, if you recall our previous answers from the answer in question A, your potential at point A is negative 18 volts, and potential at point B is negative 10.8 volts. So it will be the work done here. So the work done from A to B divided by the charge is equal to VA minus VB. And we are to solve for the work done. So we need to transpose this one to the other side of the equation. Then that's work done from point A to point B is equal to charge times VA minus VB. Now substituting our values, the work done from point A to point B is equal to, your charge here is 2 times 10 raised to negative 9 coulombs, times your VA is negative 18 volts minus negative 10.8 volts. What will be our answer here? We have work done from point A to point B is equal to 1.44 times 10 raised to negative 8 joules. If you input that in your calculator, you have 2 times 10 raised to negative 9 times negative 18 minus negative 10.8. So you have approximately 1.44 times 10 raised to negative 8 joules. Now let's look into another problem. For charges, Q1 is 5 microcoulombs, Q2 is negative 3 microcoulombs, Q3 is negative 2 microcoulombs, and Q4 is negative 6 microcoulombs, are situated at the corner of a square of side 5 meters. So this square, each side is 5 meters. Find the potential at the center of the square. What do we need to do here first? We need to identify the R between this point and the charges that surrounds it. And since this is a square, all of these r's will be equal to each other. And how do we solve for that? When we look at our illustration, we can easily solve that by creating an imaginary smaller triangle. So if this is r, and we know that this side, one side, is 5 meters, if we make an imaginary triangle here, we know that this side will be 2.5 meters, and this side will also be 2.5 meters. Now, in this triangle, we have now the two sides, and we can solve for r, which is, when you look at the illustration, it'll be the hypotenuse. We can use the Pythagorean theorem, where r will be equal to the square root of 2.5 meters squared plus 2.5 meters squared. And that will be 3.5 3.536 meters, so approximately 3.536 meters. The r for all of the four charges will be 3.536 meters. To solve for the potential, we just need to solve for the electric potential that is due to the four charges and then take its algebraic sum. So to solve for the potentials, we need to solve for the total potential, the potential at the center of the square. It's V is equal to V1 plus V2 plus V3 plus V4. And V1 is equal to KQ1 divided by R1, which is 9 times 10 raised to 9 Newton meter squared per coulomb squared, multiplied by the charge for Q1, which is 5. It's micro, so you can write that as 5 times 10 raised to negative 6 coulombs, divided by 3.536 meters. So our V1 is 12726.24 volts. Now V2 is KQ2 divided by R2. That's 9 times 10 raised to 9 Newton meter squared per coulomb squared, multiplied by the charge for Q2, it's negative 3 times 10 raised to negative 6 coulombs, since it's micro, divided by 3.536 meters. And that will be negative 7635.75 volts. For V3, that's KQ3R3, which is equal to, of course, your K is 9 times 10 raised to 9 Newton meter squared per coulomb squared, times, you have your negative 2 times 10 raised to negative 6 coulombs, divided by 3.536 meters. And that will be negative 50905 volts. Now for V4, let's squeeze it in here. That's KQ4 over R4. And that will be, of course, 9 times 10 raised to 9 Newton meter squared per coulomb squared, multiplied by the charge for Q4. So this is Q3 and this is Q4, which is 6 times 10 raised to negative 6 coulombs, all over 3.536 meters. So your V4 will be equal to, if you input that in your calculator, that's 15271.5 volts. So since this is electric potential, so our unit is volts. But when you look at it, when you cancel it operationally, so you're left with Newton meter per coulomb. And Newton meter is joules, and joules per coulomb is volts. So we now have our values for V1, V2, V3, and V4. So we just need to take its algebraic sum. So let us rewrite the values based on our previous answers. V1 is 12726.24 volts. V2 is negative 7635.75 volts. V3 is negative 5090.5 volts, and V4 is 15271.5 volts. To solve for the potential at the center, so V center, let's say V center, that's V1 plus V2 plus V3 plus V4. So we just need to take its algebraic sum. So V is equal to 12726.24 volts plus negative 7635.75 volts plus negative 5090.5 volts plus 15271.5 volts. So the electric potential at the center of the square will be, so let's input that in our calculator. So you have 12726.24 plus negative 7635.75, and then you have 1726.24 negative 736.75 plus negative 5090.5 plus 15271.5. So what is our answer? Our voltage or potential electric potential and potential difference. Basically, again, electric potential is your electric potential energy per unit charge, and your potential difference is the difference between the electric potential at 2 points. So thank you very much for listening, and see you next time.